and I'm thinking, I've worked with Microsoft.
Okay, so thanks for coming out. We are broadcasting on Hangouts now as well as doing in person. So hopefully the Hangout people can hear us. Throw us a comment in the YouTube chat if there's any problems. I don't see any of you actually online yet, so we're talking to nobody probably. So this is the second meeting in the Python data science. I think all of you guys were here before, except for maybe Chris. And we're going to just kind of go over the reading that we did and go through some of the data sets in the UCI big data area. We'll touch a little bit at the end probably on kind of our thought around a challenge, which is a very loose thought. It's a little open for discussion about how we want to apply the learning that we're doing. So we want to do more than just read. We want to have some sort of exercise that you guys can do to apply what you're learning, and we can all kind of work on the same big data set and perform the same algorithms and maybe discuss the results and that sort of thing. So that's what we're thinking about for a challenge. Has anybody never been to TIG? You've all been here, right? Oh, you've never been to TIG? Okay. So for Chris's enjoyment, we'll do the spiel quickly. The idea behind TIG is really just a nerd book club. We all meet and usually pick a book and read together over multiple months, and we want to get more depth out of a topic than you get from a typical user group. And the idea is really that it's driven by whoever's here. So we want it to be very question-based. Ask all the questions that you have. There's no dumb questions. We want everybody to participate in the discussion. So please ask away, even if you weren't here last month, you didn't do the reading or any of that stuff, just have questions that will help drive the conversation. I think Chris has got some notes on the reading and some ideas of where to lead the discussion, but really it's up to you guys. So take us in whatever direction you want. And that goes the same for those of you online. If you have questions, we'll monitor the chat. Just go ahead and throw them in the chat and try to get those in order.
Did you want to play?
Any other questions in general about TIG or high-level questions before we get started? All right.
Thank you, pizza.
Yes. Of course. You're welcome. Sorry, people who are online.
It's delicious.
Yeah.
Always.
DJ Slow Pans. He made it for us.
You can give them virtual pizza.
Serious. Just Google DJ Slow Pans. You'll enjoy it. All right. Chris, it's all you.
Okay. So the first chapter was mainly just an introduction and talking about kind of what we'll be covering. And we kind of did that last time. So the main thing is that we're talking about regression and classification as the two main algorithms that we're going to focus on. So let's see. Is there any question about what regression or classification is, as far as those books go? Or yeah.
I just, regression, I always consider like the classical statistics we got taught in high school, right? It's like fitting the best line to the dots, using the least mean squares to figure out like, what's the lowest error possible, and that's it, right? And it seemed like what the guy was talking about in the book is like, okay, great, regression has, we get a lot of mileage out of this technique, it has a lot of applications, and now that we have like really powerful computers, we can, out of a data set, do lots and lots and lots of regressions and take averages over those regressions and get an even better, more reliable fit in more conditions. It seems like that's sort of the bottom line is what he's saying about penalized regression methods.
Yeah, so there are a couple of things there as far as regression goes. So there are different methods for regression, right? So the traditional linear regression is just drawing a line through a set of data points, actually, is what we have on the monitor right now. And sometimes that's not good enough, so we want to be able to create a more complex line or fit a more complex graph. And then some things, maybe regression on a set of data, multi-dimensional or hyperdimensional space. And so you might not just have a 2-coordinate system that you're trying to regress on. And the traditional statistical models, the most commonly used one is the RIMA model, I believe. And so that one's just a set of functions that produce an output value. the big difference between the regression that we're going to be doing here and a regression from a equation like that is that we're doing a little bit more complex of a interaction. And so random forests, for example, they'll still essentially do regression, but they're based on decision trees. And so you can have a random forest regression that's in scikit-learn, and you might get values that are based on that. And so the best example of that is neural networks. And so neural networks will make decisions based off of based on it'll do classifications, but we could classify even to a binary value or something along those lines and do some extremely complex form of regression in the end. And so the more accurate that people try and get with these techniques, the more computational power they'll throw at it. Stuff like the support vector machines, they typically take less computational effort for the amount of AUC, area under the ROC curve, that you get out of them, things like that. So each of these techniques may or may on big data sets may or may take much longer or much less time and have kind of trade-offs. I think that's what they're trying to say in this area. So the penalized regression is another one of the techniques that he pulls from this. But if you look at the scikit-learn libraries, there are actually quite a few more systems that he can be using. So like sklearn, and he talks about it in this book. And in chapter 2, he begins using. I just love using this image right here. So these are the different the different systems that you can actually do regression on and get widely varying results for individual values. And so trying to fit better can take the different algorithms. So yeah.
And when you say do regression,
Yeah.
what you're saying is that essentially for any one of these techniques, we're going to end up with a set of results.
Yeah.
And a set of result sets. And that regression is what we would run against those results to get the best possible result. Is that the idea? Or
You're trying to get a model, right?
Mhm.
You're trying to get a model that can answer a question.
Yeah, predict the value.
And so these are ways of deriving the model.
So rather than thinking about it of using regression to get a data set and then you use regression and the output value of the regression or classification is going to be your target value, your ultimate destination. You want to fit to that as closely as possible. So when you talk about it's not really more complex than that. So in the second chapter of the book, they talk about identifying the most relevant columns to the data set and eliminating noise. And so that's a big part of it. But
That's part of the penalized, right?
Yeah.
That's
you're removing now the you're saying that this piece of data is less important than this piece of data, and so on and so forth. So like decision trees, what they do is they actually have a entropy model that happens for different pieces. So if you go in and look at how to actually build a decision tree, you don't just say, okay, take this feature and decide on it, and take this feature and decide on it. You start with a feature, and then you find, using an entropy calculation, I don't remember the equation by heart, but you decide that which is the next most important feature to make a decision on. And then you entropy again, and then you decide what the next most. And so what random forest does is it creates basically a tree maybe for each feature with the root of it at each feature with the different entropies, and allowing you to get a model that can make more complex decisions. And then that's kind of, so you can kind of see, here's a decision tree, and then here's a random forest. And so it has certainty based on the trees in the forest, where The decision tree has very hardcore certainties to it, and that's all based on whether or not you use one entropy calculation or many entropy calculations. And so the random forest model is actually an ensemble model, meaning that you take a bunch of some less complex models and bring them together to make one big one. So I don't know if that.
So what about applying this to kind of like a real world example? Like last month, we looked at the iris data set. One of the things we found in applying the algorithm we were applying is that there was actually some columns in that data set that didn't matter, right? It didn't make a difference in the ability for it to.
And that's basically that second chapter gives you methods of eliminating those. And some of the methods, especially in sklearn or libraries that are more developed, they just automatically do it before they even run the model. And so you might not know it, but the system that is doing your prediction, the model, may have already dropped the columns by the time it actually runs through the model.
So when we talk about regression in that context, like in the context of the iris data set or even penalized regression, what exactly are we talking about?
Well, so when we talk about regression, we're predicting on basically an ordered or set of ordered values. So like the number line, right? You're making a prediction on a number or something along those lines. When we talk about classification, we're building a model to predict, red, green, blue, like single solid values that have no ordinal relationship to each other. And so, yeah, it's good to make that distinction. So when they talk about the two methods, they're basically splitting it into the two categories of machine learning that typically happen. So like typically, neural networks are typically used for classification because it can predict true or false values. There are ways to make those into regression systems by having them predict binary values and then computing that into a numeric value, things along those lines. Then all of these different systems here could be applied to either regression or classification. Decision trees are typically classifications, so they might be just classifying these areas. But you could, as you can see here, you actually have a classification on basically any value on this two-dimensional plane here. And so you can say that right here is going to be red, just because it's deciding based on the position there based off of the original predictions. K nearest neighbors is typically done through regression because you're just taking K nearest neighbors uses the distance algorithm. So a squared plus b squared, or square root of a squared plus b squared is the distance, right? And it uses that to assess the distance from all the other points around it. And then it uses that to make it, so if you have three nearest neighbors, you're saying take the three nearest points and make a prediction off of that. And so you can customize these algorithms in there. So making the distinction on the result of the problem is important. And there's some algorithms out there that'll do both at the same time. So you might be you might have 7 input values and then 3 output values, and you might be able to predict a class in a numeric value and another class as the output for that algorithm. So it just depends on how they're structured as you go forward.
How do you drop? So if there is a variable which is a function of, say, linear combination of 10 parameters, and 2 are very important, third is less important, others are extremely less. So do you do principal component analysis, or how do you drop those things?
Well, it just depends. So if you're trying to predict the values on a line, we actually could do that as an exercise. That'd be a great one to do. But basically, if you have a linear function, an exponential function that you're trying to predict on, you just have the inputs of your coordinate system. So for simplicity's sake, we can talk about a two-dimensional function. We could actually add noise, and I've done this before. We can add noise to the input value, and then we can have the inputs be the x and y coordinate, and then noise attributes, and then you can put that into any one of these regression models, and it should, and you can take random points, random x and y's, and then have this system learn it and then plot it out for all of them. It'd be interesting to do, and we could probably do that, but we probably should talk about the chapters themselves before we get into that. Any other questions?
I'll just make an observation.
Yeah.
So there's a local meetup that's a predictive analytics group.
Mhm.
And the guy who runs it gave a presentation last month. And the beginning, the first 15 or 20 minutes of it was talking about the most used methodologies in data science. And he was saying, basically decision trees and random forests and regression are like, covered in most books. And he says he himself, in echoing what this author said, like basically 80% of his work is done with one of those two techniques.
Yes.
So it's interesting that there seems to be a consensus in the field about where the most bang for your buck comes out of in terms of the techniques.
Yeah.
In fact, these guys, like the paper that he references right in chapter 1, I can't remember. But he references a paper where they took like a ton of different problem sets and figured out the best algorithms, and decision trees were always number one, right? Like, what's this? I didn't find the name of the guy.
For my master's thesis, I did I produced a system that used genetic algorithms to automatically, go ahead.
I'm sorry, just Rich Caruana, right? That guy.
Mhm.
He and his grad students basically, ran, 10 different algorithms against, a number of different data sets. And as you're saying, the decision trees and random forests seem to just top the list, pretty much every time. It's a rare situation where, another algorithm would beat it.
Interesting.
It's in table 1, 2 on page 4, actually.
Thanks for sending me my thesis, Jim. Last
Oh,
time.
yeah.
So that was really helpful. Let me try and find it. So I created so genetic algorithms are pretty intense. But one cool thing that you can do is they can try lots of different things and find great optima and very complex problem sets. This is just the code.
Yeah, putting all that code in there really makes your thesis look thick.
Yes, it does.
20 pages for a thesis. Oh, 40 pages is just copy and paste of the code.
About 100 now.
Nicely done.
No, they asked me to do that. I had no choice, really.
Call it appendix.
Imagine back in the day when there was only punch cards, how thick your thesis would be. Massive.
All right, so let's see, that's accuracy over default SVC. Okay, so this was a cool thing. So this is a genetic algorithm, and basically what it was doing was it was eliminating error. Well, I was actually optimizing AUC. So so the area under the ROC curve created a what's called differential evolution binary particle swarm optimization. So it's a form of genetic algorithm.
What else would you use?
And what it does, it actually takes an ADA boost classifier, a C-support vector classifier, gradient boosting classifier, so on and so forth. So everything up in that top corner there, and compares their performance. And so on this problem set, which was basically facial recognition.
Oh, cool.
We'll kind of try and see. So we have varying levels of difficulty in those. So the face is turned in different ways. Depending on various, so you're supposed to be able to detect, the face even in that 6th difficulty where the person's like turned and farther away or closer and so on and so forth.
And then a little known fact, this algorithm utterly fails if the head is not disembodied.
Yeah.
It's called overfitting.
So what we try to do is the forensics tool, Jim, and we expect the head to be disembodied.
Decapitate the victim first.
Right. Then embed his head in rocks.
Victim or test subject, depending on how you. So what this does, so ultimately though, what it did is it actually tried the data set again with different configurations of these different systems, because even if you have a random forest, there's actually plenty of parameters you can change in the random forest, even how it does its entropy, how many leaf nodes it can have, things along those lines. So,
Cool.
So you can do some massive configuration on different systems. And so even though, so it's one of those things. It's just like security or something along those lines. It's one of those things where you can spend an unlimited amount of time basically configuring and making better. And so you have like some point of diminishing returns in which you want to continue configuring. So that's why this is becoming such a big field, is because you need to know a lot about statistics and things along those lines, and also the programming portion of it. And so there's a small niche of people that actually can fulfill that, but then they're just running experiments all day trying to figure out better and better ways to identify junk mail or predict weather patterns, or what slice open an abalone and figure out what's inside the abalone. Yeah. So in the second chapter of the book, we're talking about, it costs $1,000 to slice open an abalone or something like that, and it takes a lot of time. So they just want to measure them to figure out how old they are. So that's kind of the gist of that. So there are all kinds of ways that you can configure those things. And a great little section here is so like multi-layer perception might not be the best.
So how do you decide about the difficulty level? Was it by you estimating what the image looks like, or by the fact that the results were so worse and worse and worse?
Whoops, what just happened?
Wasn't
I just lost my thesis.
Don't worry, Jim has it.
Yeah.
okay, so yeah, your thesis is
That's pretty cool.
wasn't that based on previous uses of this data set, like how they are decided the difficult?
Yeah. So in previous papers, my reference material, what they did was I want to just show, okay, so the difficulty was based on these factors. It was the orientation. So like, are they looking up? Are they looking down? The vertical and horizontal positioning in the picture, and then the size. And so if you varied that a large amount, so can they take your Facebook photo and then tell when you're walking into a supermarket so that they can relate your Facebook profile to the supermarket record to be able to recommend things for you to buy? Well, in order to do that, you need to be able to say, take multiple images from all around this person's face and identify them no matter where they are or what they're doing, and confirm that it's that person. And so you have basically, you build a model for each person, and it says, okay, well, confirm or deny, is it that person? And so so this is a classification algorithm ultimately to say, yes, that's the same person. And so as a more extreme version of this, we also look at cars and planes. And so you can kind of see there's like a car flying over a mountain right down here. It's pretty fun.
Yeah.
And so
Like there is.
Utterly fails to find any cars on road.
Very useful for flying cars over mountains.
This is a
other ways to
daredevil
possible spot.
detection system. Thank you very much.
Dukes
We
of
detect
Hazzard.
only daredevils.
Yeah, exactly.
So the first one when detecting faces, that's effectively what Facebook is doing, right? Like they have the system that will say, this is you.
So
It used to say, is this you? And now it just says, this is you. I know.
yeah,
This is
so
you, don't say
No,
no.
it's not. Yes, it is.
So MIT came up with this way of translating the data, basically. So they take the raw image, then they take what are called Gabber filters, and so it detects the light variation between the horizontal, diagonal, and vertical positions of light in there, and then it creates these multiple layers of data. And so this ultimately every image ultimately boils down to, so if you have a 220 by 220 picture, that ends up becoming 4,000 data points that you then can classify on. And then regression will then do something, or classification will do something to that and then spit out yes or no, that's the person or not. And so so what happens, it gets Gabber filters, then it takes the local maximums to kind of prune that data set. Then what it does is it sets up a prototype dictionary, which are a number of other models to be able to detect them from like a certain position if they have similar. So they remove the positioning of the image by creating a prototype dictionary, which you can detect whether the face is in like this portion or this portion or this portion, and they do that for 11 pixels, 32 pixels, 100, 220 pixels. They widen the scope of it, and then that gets translated into that C2 layer, which is the maximum activation of those prototypes. So now we have a 4,000 long string of data that allows us to then predict on, run classification on. And so the very last column here, of course, is going to be, yes, it was that, it's this person or not. And so in this, we had basically a male decapitated head and a female decapitated head. And we were just detecting between them. But, ultimately you get more confusing data sets to prove its viability. So
in that
Boulders.
in that example, we have like 4,000 features in one label, essentially.
yes,
Yeah.
yes.
Wow.
And so you don't want to do that math by hand, right?
Right.
And so and to get there, to produce that data set, it's actually an extremely long process because the Gather filters will take that 220 by 220 and just blow it out to a huge number of records, and then you're supposed to compress that back down and then blow it out and compress it back down. And now you have sufficient amount of data in each one of those points to be able to predict on that.
So that's kind of what the author was referring to, and he's saying like 80 to 90% of your work is going to be like getting the data ready. And then once it's ready, it might take X amount of hours to run your algorithm, but all the work is going to be in data prep.
So I like and I dislike that statement because in a lot of, you might have data that is just ready to go and you can just try. Like if you could throw something in a support vector machine and make a prediction on it, like that might be good enough to start getting like 80% or so. So one thing that Aaron and I tried last year was predicting the March Madness numbers because of the victory thing, and so we just took a bunch of get me data sports yeah. So I told you I'd keep you interested in this time. And so what we did is we just took a bunch of data about the teams and threw it in there. We were getting like a 70 something plus accuracy. But that's not a good AUC, and that's not good enough to predict the March Madness brackets. So then you're going to be spending your time finding better data, predicting it clean, or verifying its usefulness to the data set, cleaning it, and doing complex transforms of it like this one. So this is this actually used thousands of models to produce each of those data points, which then now contains some information about what we're trying to predict, and then therefore can be used to do those predictions. So typically Facebook will get an image, they'll run this huge pre-process to it, and then once they have prepared it, then they can start learning it, and then they can learn who you are based off of.
Yeah, so in that facial recognition example that you're doing, like in a practical application, like if I was, the FBI or the police department that's got all these cameras in public places that are constantly recording.
Yep.
When they want to ask that model a question, they want to ask it, is that this person, right?
Yep.
So what are they feeding it to say, this is the person I'm looking for?
So they take that image and then they do this pre-process to it to get those 4,000 records, and or the 4,000 features, and then they feed it the 4,000 features.
So they say, I know this is the person. Can you find this person in this other data set, basically?
Well, typically you'll have a model per person you want to detect. So you're only getting a yes or no answer in this model. Like there are others so this is the one that was developed by MIT and is pretty widely used for facial recognition experiments, and probably used in a lot of production areas as well. So what they'll do is they'll take that video feed, they'll probably take a sample of it, and then they'll get that data row, and then they probably have thousands of models of set for people that they're looking for, and then they can just say, there's a match, investigate, and so and then typically it'll go to a person. So that's the whole thing about the AUC curve, right? So we talked about that last time, is that you're not trying to predict accuracy, because you might get like a 90% accuracy, but if your false positives are really high, then you're going to be really frustrated with it, and you might be doing a lot of extra investigation. So you might want to remove all your false positives. Or if you're looking for a terrorist from a video bank, you might be saying, okay, well, let's reduce the number of false positives we get, or let's increase the number of false positives that we get in order to investigate more people, because and so that's again one of those things where you could spend an infinite amount of money trying to do. But you're going to want to be aware of the impact of your false positives and false negatives, because that's where the AUC score comes in. Is that the area under that curve means that given the adjustments you give it, you can get that area smaller and smaller, or the area over the curve smaller and smaller, meaning that you can eliminate false positives more and more as you set a threshold for where your predictions are going to come from.
So things like facial hair could really throw you off.
But I mean, you could have different, so this system is relying on the idea that you have, you know, hundreds of pictures of this person and you've already pre-identified them. So this data is saying like, okay, well, we had 300 pictures of this person, and we're going to feed it into a machine and then give people that look like him and say that that's not the person, and then let the machine learn how to predict, yes, that's that person, or no, that's not that person.
So with a beard and mustache, you'd focus on the forehead, the eyes, the nose, the
Yeah.
cheeks, anything that can match.
Yeah. And there's some pretty cool stuff out there.
So if you want to rob a bank, do it without a beard and then grow a beard.
But what if you can't grow a beard to that?
You can buy a beard, put a hat on,
Buy a beard, oh, okay.
buy a beard, put it on, then all be solved.
So
What
this
I've learned.
stuff's really creepy.
Oh,
Yeah.
But predict, so you can predict the bottom of the face, or like learning a face and then predicting the other half of the face. So you like learn the top of many people's faces, and then have the training material be the bottom of the face, and you use the top of the face to predict the bottom of the face. So you can remove the facial hair presumably. So like, you know, the shows where they say enhance. So that's actually like, that could be legitimate to a level, because you might have a unfiltered version of that face. You could then read that in with the low res version of the face, and then give it the high res version of the face, and then start predicting high res faces based off of low res faces. So that enhancement thing is that particular type of problem is actually being worked on now. But predicting the bottom or the top, you see they got the eyes. And that's kind of the machine creativity stuff that you keep seeing. I don't know if you, maybe that's not it.
Creativity.
Google's fixing for you.
It's not in there. What was that called?
It's like deep dreams.
Oh yeah,
Deep dream stuff.
dream.
Deep dream.
Yeah, that's
Yeah.
not. So it's like it's doing predictions off of. It's using, it's combining images based off of predictions for, this is kind of a Google research project. And so you can combine certain things by using machine learning, and then having it produce stuff based off of feeding it some inputs to get out other inputs and things along those lines. Really, really interesting stuff.
You know, a little note. I was doing an optical mark recognition system. And because I'm using Visual Foxtrot, which is kind of like Python in scripting kind of language and not very fast, I found it faster for me to actually make a loop where I would lighten the image or increase the contrast through a library which is in C, which is much faster. First to kind of tweak it, and then I do the analysis of numbers of the darkness of all the points and the contrast between them. So sometimes spending the brute force ahead of time to just lighten the whole image everywhere, or darken it to make it a contrast, because we have a scripting language after might be.
So what's NumPy doing right now, or Pandas, or scikit-learn? It's actually making calls out to C++ library.
Okay.
And so you get all that computational complexity out of the way in C++, and while writing your code in Python. That's why, statisticians who don't know how to program very well can use a very easy to use language like Python to call into C++ libraries, which will then execute the different models that you wanted to use while doing them.
Cool.
So kind of, we can go back to any other questions before I go back to the.
One of the things I'm kind of wondering about, based upon the conversation we had earlier, is like that final product, which is the actual model itself, which is going to do that prediction, which is going to take those 4,000 features or those 3 features or whatever they are and give us our prediction.
Yeah.
Is that end product always unique in the sense that, it's a functional expression of some sort, right? It's going to be unique to every particular problem that you pose and solve, right?
Many of them take randomness, and every time you train them, it randomizes the the inputs. And so, especially like the entropy for decision trees, they have a random element to them. And so a lot of the time they'll still include or incorporate random values. So each time, so once the final product, yes, it will be you get inputs and you get an output. And typically it's
And those are
always the same.
consistent, right? You'll always get the same output from.
I'm trying to think if there are any models where they're not in the end. So there's the idea, there's the practice of fuzzy logic, and fuzzy logic may still be in that realm. And so, but fuzzy logic and machine learning are a little bit different from each other, but have roots in the same area. Yeah, so there's the possibility that somebody might be fiddling with the output before it comes out to make it non-deterministic. But I can't think of one off the top of my head. But typically, yeah, that would be the case. So if you train a neural network, then the neurons will have these settings, the weights on them, and then you can now feed in any input and get an output from it. And so that output would ultimately be the same every time. But the training of that, if you made another model for the same data, is going to be different. Each model you get out of it's going to be different. And so a lot of the stuff that people, most of the, whenever you're trying to determine how accurate your model is, you typically run it, 25 times and then take the average AUC. So the average area under the ROC curve, radio operator characteristic. AUC, ROC, average of AUC.
It always goes back to tanks.
Yeah, and then it all boils down back to the tanks. Yeah. So yeah, and you ultimately, if you were talking to a statistician, if you ever mention the word accuracy, they just laugh at you and walk away. So you never want to consider really accuracy in this. You're gonna be, unless if you don't say AUC, you're gonna get laughed at. So just keep that in mind.
Because I'm wondering, is the actual final model that you're going to put in production, is it going to be like if you started by, creating 1,000 random forests and finding the best one or the amalgam of the best ones and created that as your final model? Your final model is going to be a random forest, right? And it's not a generic model. Like if you used regression methods to come up with a model, what's going on in that final product would be very different than what's going on in something that you were using random forests to come up with. Right?
Yeah. So you pick the model that you want to try, you run an experiment. So like if you're at a credit card company, you want to detect fraud, and maybe 10% of the false positives you're good with. Well, that may be a different model that you want to use if you can't have any false positives. And then you might get a higher accuracy with a 10% false positive rate using some other model. So you'd be going through and you'd be running the different models, running experiments. So one day you might, go to your boss or something and be like, I found a good one, and then give it to them. And then the next day you might find an even better one and you're like, I found an even better one. And so you might replace these regularly. And so you ultimately, if you have a neural network that you really like and it works really well for you, you'd want to store the weight values somewhere and then recall them to get back that same model that you had before. Typically, like the values that we end up having here, we configure a model and we say, okay, we can configure it, but if you want it to be identical to the way it was, typically no one really talks about just storing a model, because usually they're in memory. So like sklearn, getting the internal guts of it. There's ways to do it, but people rarely talk about it. They talk about, well, okay, let's start up the model fresh again. That's why you want to take the average like 25 times. But also, if you use the same model every time, you're at risk of overfitting the data. So.
Interesting. Is there any? As you were talking, I was thinking about incorporating the concept of unit tests. I mean, can that tie in at all?
Oh yeah.
To then just show that it's better.
You unit test you'd construct a model, right? So like say we were going to build a neural network from scratch.
Right.
So you take the statistical things that go into a neural network, you mock out your randomness, and then you will then get inputs and outputs based on different systems, on different toy problems. And then once you're ready to go, you're going to rely on the statistical theory later down the line to make sure that your correctly utilizing that model. So like, but a support vector, so any of those things could be test driven and you can build a machine learning model out of it, but you're not going to, you can always mock out the randomness.
Okay.
And you can seed the random
Okay.
for any of your random stuff, and you could unit test the whole system if you wanted to. But
Interesting.
it really from like a neural network was created from statistics. It wasn't really a computer science thing.
Right.
And so, but machine learning is the marriage of statistics and computer science.
Right.
So,
Right.
I don't know if that helped.
Well, I was gonna say, like we were doing last time, where we had the training data and test data,
Mhm.
and if
Oh,
you are, and the part that you're controlling is the model in between, right? So
Right.
with the same training data, it should be able to correctly predict this test data, right? And so now if you sub the model, make sure that still works.
Right. Okay. That's good. Thanks.
And some of the like cloud-based systems like Amazon Machine Learning do let you, after you're done training, you kind of freeze it and say, this is the model, and I'm either gonna send you batches of data to do predictions on, or like one at a time through like an API, right?
Right. Cool.
So, you're getting to freeze it and that kind of thing.
But I'm wondering now that Chris has said, how is that stored, like,
Yeah.
Yeah.
it's
Well,
interesting.
The
because-
options for Amazon Machine Learning are not, they're not as wide as scikit-learn. It's linear regression and
Right.
multi-class and binary classification.
So linear regression makes sense. All you have to store like the coefficients and the power for the powers, right?
Yeah.
Like that's easier to store.
But like we were discussing, you can cover a lot of ground with that.
Right.
And typically, like I said, you'd be measuring the AUC. So I think that it's probably in cloud providers' best interest. I'm not 100% sure that they're probably promoting accuracy and things that might give you a false happiness. I'm not 100% sure. I haven't really looked at them, but
Amazon does report AUC
Does
as like the overall results when after you're done training, you're trying to
Okay.
decide whether to keep or train again.
yeah. Okay, that's good then. And so typically, you want to be wary of that. Make sure that you're getting the AUC back, but you want to get like an average too. You want to say like run it a number of times, and then typically you just put in the parameters again. But there are ways to extract, like from sklearn, you can extract the coefficients. Oh, here it is. I found it. Yes.
Oh,
So,
Scary.
and so some of these people have beards, and so this guy got predicted on a beard sort of thing. And yeah.
or if he's just looking over a fence and you only got the top half.
Oh, yeah.
Yeah, so like this guy right here.
Some of those things got predicted to be what appears poltergeist.
In an X-ray machine.
Here's me eating worms that are on fire.
There's Hannibal Lecter right there.
Yeah, Hannibal Lecter, Bane,
Clearly from the
All
X-Files.
four of the right-hand pictures are predictions based on the left-hand.
Yeah.
Oh, okay. Good point.
Yeah, so I think it's across. Oh yeah, KNN. So extra trees, KNN, linear regression, and ridge. So
Linear regression they always have beards and poltergeists. So,
mhm.
so this is one
Flaming
example
mouth.
of where
This is
linear
this thing right
regression
here.
always works.
Yeah, so when you're talking linear regression, you're talking about lines, and so for this data set, you might regress to this, right?
Lines or
But
planes.
you never would hit the points, right? And so that's what's happening in this example, is that they're just getting a bunch of extra, they're predicting on a bunch of different things because they're trying to get a good match, and it can't. So the nice thing about, so we're talking about complex functions from earlier, and so these systems can predict much more clearly, like nearest neighbors here, you kind of see the wavy line there that you get off of like a exponential function. And so,
But this should be able to reveal the undercover boss, right?
Yeah.
So that you can't hide under any disguise.
yeah,
Okay.
exactly. Well, that's the top half. So as long as you have the top half of their face, you're good.
Okay.
And so, who knows? You might combine this and to produce a data set with the bottom half of the face, and then use that to detect people. I don't know. This is
It's
kind of like,
interesting, right? Because that's a pretty good, at least those first two columns are a pretty good example of
Mhm.
throwing out accuracy, right?
Mhm.
Depending on what you're looooking for as the human, you could interpret either of those first two as maybe being valuable to you or whatever. Like I could see that, something that a lay person would say, that's not very accurate. That doesn't, even like the poltergeist one, that doesn't look like his face or whatever. Like it could just depend on what you're trying to pull out of the data to see whether that's valuable or not. I don't know.
and so these are very simple toy problems. You might have more data from this.
It's weird. No.
That line,
That's on
yeah.
the page.
I don't know what that is.
That's a
Oh,
fine
there it's
CSS
gone.
right there.
Oh.
It's clearly a
Yes,
sliding panel with
sweet.
extra information.
This is awesome.
Anyway, so I was stoked to see that. So we have lots of great ways to look at data here. But anyway, so that's kind of what they're talking about here. Let's see, what are ensemble methods? Here, entropy sort of stuff. So this is the decision tree that finally gets made. He doesn't really talk about entropy here, but this is like a single decision tree, and then he talks about random forests in there, and then how to decide which algorithm to use. He's obsessed with penalized linear regression.
And abalones.
And abalones. Machine learning problem. He's talking about slowly improving your models, feature extraction and feature engineering. That's basically the same. So this topic ended up being pretty much the same, the second chapter. He also, what was interesting about the author is he constantly was like, oh, if you're a statistician, you might want to read the book in this order instead. And like, he'd constantly go back and be like, well, look at it from the computer science perspective, or no, look at it from the statistician's perspective. He wanted to rearrange the book depending on where your background was from. So that was a really interesting kind of side effect. I don't remember exactly where he said that, but he said it 2 or 3 times.
Is that right? There, chapter conference.
Is that?
Different readers may want to take a different path through this book.
Yeah. So that was an interesting thing in there. And he was talking about.
Do you understand why he was making those recommendations?
Yeah, because I mean, so I started as a computer scientist and went on to machine learning, and the professor that I learned machine learning from was very he I think he went from being a statistician to a computer scientist, and so it was really interesting. He really wanted to start it with the ARIMA model, which is kind of the old way of predicting like stock market analysis. So what it does is it's a model that blows out to different time areas, and so you can say, okay, take every year and then and remove the trends from the whole year. Take every month and remove the trends from the whole month of the 12 months in the year. And so this function would blow out. And so he taught it from the perspective of this. And so this is the basis of everything you need to know. It was totally confusing to me. I had no idea what was going on. And so, and it's really, it wasn't fun for me to solve this model. But what was interesting about it is that the different perspectives were really evident. And once I got to something that I really understood, I latched onto it and actually became one of my favorite things to do. But that first bit of it, when I was looking at it from the statistician's point of view, I was feeling a little bit of anxiety getting into it in the beginning. And I can see where you get that, because the statistician is likely to latch on to the more traditional models and build up from there. And the computer scientist would latch onto the code and then understand the models from the code. So the approaches are different, I think. That's kind of where I got hung up when I was originally learning it. So anyway, ARIMA model, go and try and solve one for a stock market thing one day.
You'll thank him.
You'll think. All right. So
Talk about mines and abalones and how they can be used together.
so he didn't do any abalone stuff yet, right?
Yeah, I did.
Chapter 2.
Chapter 2.
Yeah, chapter 2. Yeah. Okay, so understanding the problem by understanding the data.
problem is too many abalones.
Yeah.
So you need to find some unexploded
Oh.
mines.
All of the abalones by throwing them on the mines. Little frisbees, right? What shape is an abalone?
It's like a lamb, right?
I guess so. Yeah.
I have no idea.
Cup.
Like
Cool.
it's kind of oval shaped.
What's an abalone?
It's a secret.
The
It's
mollusk.
the thing that they make those Oscar Mayer circles out of. The bologna comes from abalone.
Ah.
The bad jokes will succeed. Do you eat these things?
Oh, yeah.
Yeah. So at Fish House
Well,
Veracruz.
No, they are entirely used for machine learning. only.
This
serves
is
no other
statistical
purpose
problem.
in nature other than to help
So
One day these will be useful.
you guys have a Fish House Veracruz around here, right?
That's a-
Yeah. So
That's
$60 each
For
one of
abalone.
these. For one of the
Wow.
What does it taste like?
Nothing. It tastes like breaded nothing.
They bread it. What makes
Yeah,
it
they
bread?
breaded it. Yeah, and so I ordered this years ago, and I never have had an apple.
in your machine learning class.
Yeah. This class will cost you $60 today. We don't talk about machine learning club.
You guys just keep the shell.
They're just so rare because all the scientists just saw them in half all the time.
All right, let's move on.
They're all
I
like
like to use the
landmines,
shells
so
for jewelry.
Yeah. Okay, so he talks about anatomy of a problem. Let's see. You kind of want to check, is it a regression problem? Is it a classification problem when you're looking at these things? So the items to check: the number of rows and columns, the number of categorical variables, and the number of unique values for each. Missing values and statistics for attributes and labels. So with the categorical values, he had bagging, bootstrap, aggregating, right? Like that was the thing that was in there. He also talked about so assigning maybe numeric values to labels, because the machine learning models deal more easily with numbers. So red, green, blue might be 1, 2, 3, but you want no ordinal positioning part of it. You're just assigning it a number. And scikit-learn has great ways of doing this automatically.
In statistical language, I've heard that those referred to as dummy variables, right? You
Mhm.
would just come up with basically a stand-in number for what's really a class, but
Yeah.
you treat it like a number in
Yes.
regression, so to speak.
Yeah. And that's basically the same thing here. And so you might have, I like using neural networks, even though he doesn't talk about it here. I like using neural networks as good examples, but in neural networks, you build up a number and then eventually it fires and there's a threshold. Once you pass that number, it goes from 0 to 1. So it's like a binary predictor. And so, in those cases, if they have ordinal positions and you're using like some sort of thresholding to classify, you may end up messing up your system by assuming that there's an order to it and things like that. So you want to be aware of, make sure that the model that you're using is not paying attention to the ordinal value that you're trying to predict, especially if it's trying to interpolate. Interpolating between maybe 3 points versus saying that these are actually 3 different classes. I don't know if that makes sense. So what did he talk about? So first he talked about the rocks versus mines. And so this was kind of, is it a mine, right? And so that's similar to the image prediction. And so we can go and look at, wow, that wasn't what I wanted.
You're like on page 26.
Nope.
Control G 26.
Control G, I think.
I went past 26.
No.
No, that's the wrong.
The actual
Book
page.
page number. 26. Oh,
Yeah, that's what I'm talking about.
26 plus.
Oh, if you get it such that there's only one page on your page, then it should be 26, right?
No, because
Oh,
there's a bunch of
'cause it
appendices
doesn't
that are
start
XXI.
Right.
Here we go. So we're page.
Well, figure out what page one is.
60.
62.
Yeah, what's the
66.
offset? So 63
We're on 63 now.
is really page 29.
Already brute forced
Brute forced it, buddy.
Yes, but now for future reference, it was 63 to 29. Okay.
Come on. What's going on? %20 here.
Cool.
Boom.
Back in the matrix.
Yeah. So that's the data for it. And let's see, we want to look at the values, right? So box, names, lines. Sonar mines versus, okay, so this is the description of the data. So like when you're looking at these for the first time, he kind of went over some of the, he glossed over this information and then said, trust him at that point. And so you need to read in here to find out, what you're actually trying to predict ultimately. So let's try and find out what he was trying to do from that code. If I can actually find the book again. All right. So he loads up the data. URL open, arrange data into lists of tables and attributes. So yeah, see, like NumPy would have done all of this in one line. So like that's when they were talking about the code being really verbose. And then he kind of spits out, okay, well, we now have 208 rows of data and 61 columns. And then I guess so what was cool about this was I didn't realize, he actually uses the UCI database. So that's a really cool thing to pay attention to is the machine learning databases. Oh. Oh. So sometimes they have great pictures. Oh yeah, here's the abalone. Oh no, that's the other one. Abalone, here it is.
Yeah.
There are your abalones. So these are the number of papers published based off of this data set.
Wow.
So if you're really interested in abalone, you can just go, you can start reading up on it. Machine learning on abalone.
Fish House Veracruz.
Or spend $60. Measure it first, because it's costing them $1,000 each abalone to cut open or something. Anyway, okay, so he's just reading it out.
You can save a lot of money at Fish House Veracruz. It's only $60.
So yeah, they have some like they figured it out.
Or are you really getting abalone?
Yeah.
I think Fish House Veracruz has an expert machine learning scientist working in the kitchen. I think that's
He's like, oh, there's another one.
That's why it doesn't taste good. He's a machine learning scientist. He's not a cook, right?
Does it taste like chicken
Throw
or
it in
something?
a shake and bake and you're good to go.
This tastes like crap, but it's always an abalone.
Yeah, I really, so if you guys do like find yourself super tempted to taste abalone, I'd be really interested at the next meeting to hear your experience. So everybody go try an abalone,
It's like
come back here.
2-3 blocks from here.
Yeah.
Wait, let's just go now.
Attrition rate just went up.
Yeah. So okay, so he moved on. So all he did was he counted the data, and so he was like, oh yeah.
Not on the menu anymore, man. Not on the menu anymore.
Is it really not? No,
They
come
lost
on.
their machine learning scientist.
I thought it was
Go
there.
in there and tell him you know Lucian.
Yeah.
Yeah, I know again.
Well, that's how I get my kickback for promoting abalone so much during this session.
This guy is there
That's
for
just
his
man.
base.
No, that was Chris's side business. He's
Red
an
Lobster.
abalone wholesaler.
Red Lobster got caught. They were selling supposedly lobster, and actually they were just langostinos.
Yeah.
Yeah.
But they were pricing it at lobster.
Interesting.
I mean,
Machine
you're learning
learning
it
is
just
crap.
Machine learning. Yeah.
Rubio's got in a lot of trouble for that too.
Yeah, I remember it's called them lobster tacos, and then people said langostinos, not lobster.
What's the Spanish word for lobster?
It's a different breed of
Oh.
lobster.
It's slightly
It's like
different.
spiny lobster. It's
Oh,
like,
okay.
It's like what you find here on the West Coast.
Okay,
In Baja or whatever.
interesting.
You can get them at Seaport Village as of 2008.
Abalones?
Yes,
That
So-
you can eat, or just like the shell
to
that,
eat at that fish market at Seaport Village.
oh, it,
I think the Fish House Veracruz in San Marcos usually always has them. So I always go look at the price and be like, and then
and then you realize
Order
it just
trout.
tastes like breaded nothing. Order
Yeah.
trout. Can I have the cheapest thing?
yeah. Okay, so now so first example, he just counts the rows of the, and he talks about the rocks versus mines data set. Second group, so is that sonar all still? Yeah, so same data set, but now he does a little bit more. And so so contents of the Python file. Did anybody run this code? Anybody get a chance to run it? I ran a few of them, but okay.
And you can convert them all to 3.5.
All of them.
Yes.
All right. Hear that, Scott?
Yes.
Only the first few that reference the Earl directly have a little bit of recoding. That
Oh,
needs to be
a
done.
tweak that you need?
Yeah. The rest of them are all straight over.
So you know, two years ago, it was just ridiculously hard to do any machine learning in 3. So it's basically gotten a lot better. Actually, a year and a half, less than a year and a half ago, probably. No. Yeah. So since then, I think the world. So even in the book, he says download Anaconda 2.x and do all this. So, but yeah, it's best to work in 3 now, and all of the relevant libraries seem to have been moved forward, as we were talking about earlier. Yeah, and Scott's very excited.
Yes.
We'll see if we can get through the whole book doing 3. All right, so let's see his instance. So he checks the data contents, number, strings, other. So he wrote an algorithm here to check if there are strings, numbers, or other types of columns, and just verify them so you can see. And then on 60, column number 60, it was all strings.
Yeah.
What is that about? Oh, yeah, yeah. On
Label or something.
yeah, the last bit. So he found R, it was R or M, right?
Yeah.
R or M, yeah. Rock or mine. Ah, I understand now.
There you go. You can also get abalone and then Sonata. You want to go top of the order.
I don't know.
Is that like the only place you can get it?
No,
It was so gross when I
No,
tried
no,
it.
I looked it up. There's the top, what is it, the top of the
Fish market, yeah.
fish market or
We covered that, yeah. That information is from 2008 though, so.
No, I found one that was more recent. You
Okay.
can still get it.
Still some. Confirmed. You heard it here, guys.
Any food you guys want to research for next month?
Yeah, I take no responsibility for anybody getting abalone poisoning or whatever. It's not like a blowfish, I think. So we're okay. All right. So the next bit.
So that seems like an almost trivial exercise for this particular data set, but this is an important methodology to keep in mind for like crazy data sets you're going to get off the real world.
Right, like,
Yeah.
like we have millions of rows of data, or millions of observations, I should say, and 900,000 and you get an NA and your thing blows up and you have to start over again. Yeah.
But one big thing that he talks about earlier is stratified sampling. And so you might have, millions of records, but you may only want to look at like 40 of them. And so when you talk about how much of the data you want to incorporate and verify that you're not overfitting, you might save yourself a lot of compute time and a lot of sanity by performing stratified sampling and limiting the number of records that you're actually looking at to a smaller number. And so that just means that you partition the data into groups, and then you do a sampling of each with an even distribution from each sets of groups. And so when you do a stratified sampling, it actually greatly simplifies your data set. So these data sets that we're looking at here might just be after a stratified sampling has been done, and then machine learning then kicks in. And so some of these data sets have been a little bit pre-prepared, some of them haven't. But you still want to look at this stuff because you want to understand, are any of them strings or numbers? How do they equate? And eventually you're going to do the bootstrap aggregating bagging to basically apply labels. There's also like one of n. So there's a function inside scikit-learn to automatically do that to your data. But again, we're dealing with kind of more verbose code here. Okay, statistical summaries and categorical attributes. So here's output here. Mean, standard deviation. a lot of these I typically end up just jumping into when I'm doing this kind of stuff. I just kind of open up with running a machine learning model on something and then seeing like, did I get any reasonable response from this? If not, now go back and learn more about the data. So there are different ways that you can do that. It's more of a brute forcey way to do it, but
It's called machine learning.
yeah. It's called machine learning, not me learning. There are different approaches to it. I mean, I believe did he say he started as a statistician or a computer scientist, you know?
No,
I feel like he's taking a more statistical approach here. He's saying, okay, well, what's the mean? What's the standard deviation? What's the boundaries? Things like that. I kind of throw all that out the window. I start off by running the model, seeing if I can predict something reasonable out of it. And then if not, then I go back and say, okay, well, let's start to learn more about it. Because if I can predict something accurately right away, then that means that there's some strong correlation in the data, and I might not have to do a lot of this pre-processing portion of it.
Yeah,
And so there might be a pre-step.
Yeah, so like, and even he's kind of saying that, like, well, then you figure out where some of the outliers are, and then if you have a problem, you'll know where to look. It's like, but you don't know if you have a problem yet, right? You have lots of outliers in something that's got no correlation to yours, right?
So learning how to look at these outputs and then finding, like, knowing what to do when you see these outputs for these little scripts that he has here would be great for just preparing a new data set that you know nothing about, and just seeing things, you know.
So not to totally put you on the spot, but if you were to take that mines versus rocks thing and throw it, like what would be your first couple steps? Can we jump into code and do a little bit with that data set?
Yeah, absolutely. So let's see. I would so lots of brute forcing, don't judge me here.
This is the practical machine learning.
Yeah, there you go, the practical experience.
Oh, we're going abalone, huh? All right.
Oh, sorry, not abalone.
Can't help
Going through rocks versus
Can you tell us
mines.
how much an abalone costs in today's money? That's the key.
Actually, there is something in here to predict, like, what was it, the price of rental properties or something like that? I'm like, you can apply that to abalone just like everything else. All right, so what were we looking for? Rocks versus mines?
I'll eat these so they give it back.
Supervisor says that there's a French restaurant in Solana Beach. Pamplemousse Grill.
Pamplemousse.
$4 signs.
Pamplemousse is very good and very expensive. You got to get the truffle fries at Pamplemousse. It's delicious. But when you go to the
Why did
fancy
they
restaurant
call
just to
it-
buy fries, they look at you funny.
Oh man, what am I doing?
All I want is the fries, man. I wore my tie and my suit. Just give me my damn fries. Came all the way here for the fries.
All right, so we got this data, right? And let's see, what is with
So much bad DPI scaling going on right there.
Yeah, I don't know what's going on there, but let's just say,
So you would just kind of grab it and throw it in your text file locally and then just play around with it basically.
yeah.
You can download it.
Python. But I'm watching his brute force method.
By the way, it said that he has a bachelor's, a master's in mechanical engineering, a doctor of science and instrumentation, and an MBA. Then he got
So he's all over the place.
then he got into machine learning.
He
Yeah,
loves
yeah,
learning
Yes,
in
Yeah,
all of its
loves
forms.
learning.
not just machine.
Yes.
Right.
All right, so we already kind of know, like, you'd scan through, oh, hey, there's, you can do a cursory look to see if there's any blank data, but there's no real, like, you can tell right away that that's not the case here. So we did our earlier one, right? We did basically the same thing. So maybe we just take this, we have some boilerplate thing that we did from the last example.
Oh, and one thing I don't know if everybody caught, you posted to the meetup the GitHub link.
I
right?
did,
So
yeah.
all these
This
posts
code's
from
up
last
there
month's
right
on
now.
GitHub, and it should be a link to the meetup, and this month's stuff will be up there too. So you can get all these examples. Go home.
So we're using NumPy. We have Iris here, right?
Font there.
Bump font.
Let's see. There we go.
Well, that's as far as it goes.
So that's cool.
Happened here. Are we getting the weird highlighting? Rocks versus mines not found. Oh, because it's not .txt. Is that what's going on?
Yeah, .py.
It's
Oh,
not
no.
even that. It's just
Oh, yeah,
nothing. Got nothing.
extension, that's right.
Whoa.
Well, you're pulling out certain columns that I don't, in line 19 and.
They're doing a bunch of
nine,
weird slicing and stuff that we were doing for the other data.
Oh, we tried to predict based off of nothing, so that was awesome. All right, so in here, so again, this is all ordered, right? Like they didn't actually randomize it. So one thing I might do to save time,
Or actually shuffle, right?
Yeah, we already did the shuffle.
not beforehand though. Oh, so
I think we are, didn't we have a long
Yeah, we
debate?
did a long debate and we did shuffle ahead of time.
Win the shuffle.
oh no, I'm talking about. If I can get to that last column. I'm just saying replace this with a 1 or a 0, and then you don't have to deal with converting the number, right? Brute forcing it. There we go. 1. No, probably a 0 would be better there. Okay, this is a mine, right? 1's a mine. Enough. All right, save that.
Yeah, but I think.
And then,
some of the issues.
yeah, we want to take the shape, right? So it's 208 by 61. So in here, of course, occurrences, and that's going to be the last index, last feature index, right? And then
That won't be 3, right?
No, that'll be 216.
oh wait.
208.
I did my slicing. Oh no,
Because
sorry,
it's
that's not it.
zero-based.
Yeah.
So that's what we get for magic numbers in our code,
Well,
right?
there's 208 observations, there was like 60 something.
So this 3 is
Oh, that's rows and then columns, sorry. Yeah, so it's 60, I guess.
V stack load
Oh,
slicing
right.
training set 66% of the data. See, this is wrong anyway. Oh yeah, 1 and 3. Okay, sorry. So this is
Every third row.
third row, every third row, or so we can just leave that alone. Shapes. Here's the slicing I'm talking about. So this is the last feature index, which should be what?
60. So the last one is,
Yeah.
or the 1 and 0.
Like the length is 61.
What?
And so,
Oh, let's just look at
yeah, last,
Oh.
yeah, that's right.
Yeah.
208 here. Yeah, so 61. So 60 is going to be our last index,
No,
right?
if the length is 61, that's 0 to 60, the last index would be 59.
Because the last one's the feature.
The last
Yeah,
one is the
this
1
is
and
the
0
target.
itself.
Yeah, yeah.
60 is the target. Right,
Oh,
60.
yeah.
0 based though, right? So,
Yeah.
So it's 59. Because you don't want the rock or the mine on the end, right?
Yeah.
That's 59.
So 61.
61 is the length.
features would be 0 to 60.
Yeah.
Chopping off the 1, that's 59.
Yeah, he did his output 0 based anyways, so 60 is the last index.
0.1. Is that right? So the training input, training output. So I don't think that's right. Is that right? Did we print the train in and out? Train in
Yeah, we printed the shape.
and out. Yeah, but so let's print the train
That's right.
output. Just so I can make sure, right? Yeah. so-
Test shapes, okay, and then,
Says out of
60.
bounds.
60 is what we wanted. Yeah. Okay, that's good. So 60 is good, right? All right. So now at this point,
through, that was our issue. So it's
Yeah,
inclusive or
inclusive.
exclusive, yeah, that was our issue.
print AUC, not a number. Awesome. Position label. What was this? What's that?
That's the positive label, that meant
Oh, yeah,
positive label.
positive, right.
Because this was classification on the iris problem.
Yeah,
And was that 60 now?
Positive label, because those were labeled 1, 2, 3, right? So
Yeah.
positive label will be 1 in this case.
1. Yeah. Boom.
for the mine.
82 AUC for rocks versus mines. So
Not so good. You're still losing a fair amount of legs there. You're stepping on-
yeah. So that's
Aquatic mines, could be any part of your body.
So now you can say,
Just throw
Leave with your
abalone
face,
at
I guess.
So now you can say, I want a high false positive rate in exchange for 100% accuracy.
and the AUC is saying that you will have a much better you'll basically be spending 20% of your time
Blowing up rocks.
walking over the rock, avoiding rocks that are actually mines, but in favor of not blowing yourself up.
So the one thing I noticed and I guess you didn't change it here. I didn't notice you must have done it, I guess, after, because I thought we were using an SVC classifier at the last meeting, but now it looks like you've got a random forest classifier.
Yeah, and you can throw in whatever you want, right?
Right. But this is still essentially a classification problem,
Mhm.
right? And so when we go back to talking about regression, like we were talking about earlier,
Look at our result though.
you're really dead. Yeah, you're mostly dead.
That's like guessing, like, oh, is this a mine?
Yep, that was a mine. Next.
Start over.
But this is still a classification problem, and so when we talk about regressions, does that factor in here? Is there regressions we can do that make that classification, that AOC, AU, whatever that is, better? Or is this, am I not thinking about this correctly? Like,
It's a class. Well, no matter how you look at it, this is always a classification problem because you're just detecting rocks versus mines. Now, if you had, I want to predict. So if we look at the rocks versus mines description,
Like if you could say like somehow like the TNT
Sonar.
like breaks down over time, right?
Mm.
Then like how much of it is still active,
Mm.
right? Would be a regression.
that would be a regression problem. Yeah.
I don't know. I'm making up stuff about TNT right now.
Yeah.
I'm pretty sure mine isn't actually the TNT.
If that's the way it worked, like in the Bugs Bunny cartoons, then
Right.
yeah.
Hidden
Especially
units,
since
right.
this is using sonar, so I'm pretty sure they're water-based mines. You're gonna have a lot of trouble stepping on them.
Point.
Well, you know, not much.
It was the machine learning that made those warrants.
But you could still use sonar on land, right? Wouldn't it reflect off of a buried mine? That would still work. Don't leave me to be your mine detector.
Isn't
I'm
that
just saying.
echolocation instead of sonar? Is that
I
right?
think it might work. Yeah. Sonar is just sound reflection off of.
If you have mines on land, get a rat. Seriously.
Get a rat.
Yep.
They actually
I'm
train
running
rats to
around.
go and find mines,
Wow.
and then they would actually go out.
Now
That's
that's
what
a
they would-
pragmatic approach. We could spend billions of dollars on machine learning algorithms. Or for just $1 billion, you can get all the rats you could ever need to walk over mine and never write a line of code.
But they won't, but they don't, they're so light, they don't set off, they don't trigger the.
Well, that doesn't help me.
Oh, it does actually, because what they do is they train them much like drug sniffing dogs.
Well,
Oh, to
that's,
smell
so
it out?
why not just get really
That's
fat
cool.
rats that actually set off the mines and let them loose, and then it just solves the problem.
Just give those suckers some bacon.
Rats blowing up,
I'm
just
just saying.
let loose a farm of pigs, and then you have bacon everywhere, and all your mines are gone.
Where are the names of the columns? Does
It's a
anybody know where the
solvable
names
problem
of the
there.
Wasn't it that special file, the
There's a
names
separate
file?
name.
Yeah, remember all the documentation is in a separate file.
Yeah, but I have 3 different files here.
Sonar.names.
I was looking at that. It doesn't really. Problem description, methodology.
This is a week.
Was it?
Is
that it?
No, there's more here. So.
Was it towards the top and you just flew by it, or?
I mean, I just scrolled through it a little bit.
Oh, it's Golkin. It said something about that. The label associated with each record containing a little R if the object is a rock, M if it's a mine. The numbers of the labels are in increasing order in aspect angle, but they do not.
Right there. So each number represents the energy within a particular frequency band. So if you knew that there was a mine there and you knew the other frequency bands and you wanted to predict the last frequency band, you could do that. It would be a regression problem at that point.
So that's what they train the rats in, the freaking.
Yeah, frequency band.
Okay.
Totally.
They have them read this
So-
file
Check them
first.
out.
Yeah. They have them
Teaching
filed
rats
first.
machine learning is really hard.
They've got rats.
It's worth it when you're done.
But you
lot
make
of
the big
cheese
bucks
out
if
of
you can do that.
So yeah, I mean, a big thing here is that I typically go in, I find out what I'm trying to predict. I go and write something to predict it. If it's good enough, go with it. If not, then start learning more and then kind of do the process that he was doing there. I know that's like really not the way to do it, and I know it's just me being lazy and trying it. And I feel like I kind of learn more by doing and experimenting with things. And so I typically I throw the data in there right away. I play with it, and then I start saying, okay, well, let's look at what the deeper relationships are here.
I think he uses column 35 to get a really good separation.
Oh, he parses out column 35.
Yeah, because column 35 gives him, it looks like that.
Oh yeah. So he was getting some real good. Okay,
Yeah.
so
He got
let's see if 35
really
gives the same.
clear separation.
So let's see, 35 to
It was what, page 46?
44 also.
On 44 gives you a kind of a grouping, but yeah, he starts on 44.
Yeah, he mentions 35 on both 44 and 46. Yeah.
But when he actually runs 35, then he gets the plot that's on 46.
Oh,
the other
gotcha.
page.
Gotcha.
I'm missing something here. Train input, train output. Actually, we can do this. 35, 36, 30, and so you can do it this way. Input 35, 36, and then sets again, and use 34 and 36. So I eliminated a bunch of the data, right? And then still tried to predict based off of it.
Oh, but you're still using the
So-
classifier though, right?
Yeah. Well, no, I'm using
You're back to
the.
random forest or not?
I went back to random forest, I think. Yeah.
So that's way worse. But
Yeah, it's way worse. But I mean, it might be. So let's try SVC. Because he was saying linearly separable. Oh, we got a better result with. We got a much better result for the SVC than we did originally when we removed a bunch of the data, and based off of the findings that it had in the previous thing. So it does build on itself, and using an ensemble classifier right away doesn't teach you a lot about the data, because ensemble methods in general are really fast and really smart at doing this stuff, but they're computationally more expensive than, say, SVC. SVC is like the first thing you can throw at a huge amount of data and see if you get any patterns out of it. But then you get also, like, you can replace the internal kernel to that classifier. So that's when getting these. So all of these are support vector machines, both of these here, but they have different kernels in them, and so the support vectors end up coming out differently. And so there's a ton of configuration that you can do.
We talked last time about why it's C instead of N, SVC.
So it's a support vector machine classifier. So instead of saying machine, it's saying support vector classifier or support vector regressor. And so they have some inconsistency in their naming. Sometimes they call them regressor and classifier.
SVMC, I guess.
Yeah. SVMC and SVMR. Yeah, so that is a little confusing, but basically everything in scikit-learn typically has a classifier or a regressor, unless it's a algorithm that can't be ported from one to the other. And then of course, like TensorFlow is a neural network that's only going to be a classifier for you, the one from Google. And then I actually heard of a few other new tools lately, recently.
So you said something interesting there that you look at the data and run these, you may run like a brute force SVC on the data to see what patterns emerge. That's kind of like,
Just saying, is there something where, is it a no-brainer where I can just like do this right away before I spend a lot of time on it?
right. So we were having a discussion today with someone this morning that, it sounded like they had maybe a machine learning problem, but we weren't sure. And we had a rough framing of what the issue was, of kind of like, there's some users that are doing a job, and there's a quality control aspect that other people are overseeing, what their output of that job is. And they want to improve the workflow of their QC people because they are QCing people that don't need to be QC'd, right? Like there's people that are not failing at their job, and so they're performing quality control cycles, and they're finding most of the time these guys are fine. So we really shouldn't be looking here. But because they're just kind of linearly weighting people, they're just everybody gets QC'd, or just, this first chunk gets QC'd without any knowledge. What we were kind of talking through is they've got a series of data points. If I get my terminology right, I think we would call those features. There's features about a given person that's producing this workload.
Well, it's
we
a
don't-
workload, right? Who produced it?
how many times they've produced workloads in the past, how similar these workloads are to workloads they've produced in the past, how many times this particular person has been audited in the past. You know, like all of these things are features
So what would
to
you try to
basically
predict?
answer the
Yeah.
question, should this be,
Yeah, I guess that.
if we QC this, will there be feedback or something, I guess.
Yeah,
what you're
is
saying.
there likelihood that the quality control person
Catch
reviewing is worth the time? Like, this guy's like, I'm paying money to my QC guys to review this workload, and too many times they were reviewing workloads, and the end result is they didn't have to do anything, the workload was fine, and I just wasted cycles. And so the throughput of the QC team is way lower than it could be because they're wasting time looking at more data. So
Got it.
that was kind of the thought, and we were kind of thinking through, like, what would we do there? We've got these features, we got this data, and what's our first pass to just say, I just eliminated 20% of your workload right off the top because it's just dead simple, obvious, you don't need to do this.
Yeah, so one big thing that you want to do there is make sure that you have historical data for the result. That result that you were trying to predict in the future. So if you take that existing set of data and you have, okay, yeah, that was a waste of time, that wasn't a waste of time, that was a waste of time, that wasn't a waste of time, you classify them, then you have now a classifier. So you use a support vector classifier or a random forest classifier, for example, which probably would be a better option. And you just throw that data at it and then see if the random forest classifier got a good AUC. Then you could say, okay, well, I'm going to adjust the way I'm doing my predictions to include many more false positives. So, or fewer false negatives, right? So that we don't affect the quality work that's coming out of their system. And then you'd say, and then you just give them that number. That might be a 60%, sort of benefit, or a 20% sort of benefit. Whatever you do to not affect their overall quality. You want to use the AUC membership.
Workload of the worker.
So you'd find your ROC curve, then you'd find where on the ROC curve you wanted to be on as far as false positives and false negatives. And then if you say you absolutely don't want to affect their work, but you want to reduce the amount of work that they're doing, then you just go very conservative, and then you just eliminate, you use that to predict whether or not you're wasting time. If you can measure those things. So one thing is that those measurements you should be able to take those measurements before the usefulness of the prediction of the result can actually be produced. So, right, and then at that point, then those predictions are really useful to you.
I mean, like, I don't think we have an individual column right now, which basically says this was a rubber stamp, like this one one was just a pass through or not.
Yeah,
So
they
we
have
to-
some indicators that they think the following 6 things, if any of these are true, it's probably going to trigger a quality issue. So that probably means they need to be quality control, but that isn't always the case. And so it's more fuzzy than that. They have this other thing I'm thinking too, and I was originally thinking maybe this is a regression problem, but maybe the classifier just handles it, is like a given person's history changes over time, right? So we may be guessing based on your previous history, you don't need to be QC. You're good, you're good, you're good. But if we never QC you could start producing quality issues, and we have to feed that back into the model to say,
So
now
just
you're
like
causing problems.
Yeah.
Now you need to be reevaluated.
They know they're not being looked at.
Yeah, I mean, they
exactly.
wouldn't know, right? But what would happen is we want to say, we're not affecting your quality bar. And as of today, we aren't, because that person's never had a quality issue.
Yeah,
Then
so
all of a sudden they have 5 quality issues in a row, and we missed them all.
Yeah.
And so now it's like that data needs to be fed back into the training model, or there's some sort of
You
regression.
retrain based on that data. So that's kind of what I'm talking about with stratified sampling. So if you have a number of cases that are repeated frequently, then you just do a stratified sampling to eliminate the repetition of those cases. Then you'd feed that stratified sample data into your model and predict it. So like a great example is like predicting a offset for somebody's estimates in software development, right? So this is something that I don't deal with anymore, but when I did deal with software estimating, there were like Fogbugs had a great it has a great little feature that you can put estimates into fog bugs, and then you can track actual time. And then it basically predicts.
Learns how crappy of an estimator you are.
Yeah, it learns how crappy of an estimator you are,
And
and then tries
automatically
to
adjusts it for you.
digest it. Yeah, and so
But by virtue of seeing that data,
Yeah.
you become a better or
yeah.
worse
You
estimator.
could.
Yeah, yeah, yeah.
Or you
So
can just keep-
you keep it a secret from the developers that are doing the estimates. That's part of it. So they continue to give their estimates. It continues to adjust it. So that's something that's possible. Although estimates are totally bogus, and I would never use them anyway. So I just want to throw that out there.
Get on the record there.
Yeah. Just keep it on the record.
Tell us how you really feel.
Next
Yeah.
gig will be about no estimates.
Yeah. So so where was I going with that? Okay, so it would be a regression problem if you do have like a quality rating or index or something that you get out of it that you have on there. Or,
It's
So-
probably a bit fuzzy, but it is kind of like there are the consumer who's purchasing this product, right? Like they kick off a workflow. The consumer says, I want the following thing. Some human is involved in doing this operation for producing this workload, and they get the resultant product. And the person who ultimately gets that product back can find issues in it or errors in it, quality issues. And so one of the services that this customer provides is that they QC that work before it goes back to the customer, and that's a competitive advantage. But they can't QC everything, so they want to hone in on what they should be QCing to still give the customer the impression that everything's great.
Perfect.
But if our model says we've trained it with the last year of data of all of the workers that are producing this product, we've trained it, and now as you go, here's a new order, here's a person who did the work before it goes to the customer, does it need to be QC'd or not, our algorithm will run and say no, and we keep saying no because it looks like this person's good. We still need to feed back into the model the ultimate quality, and that can be a little fuzzy because they're not going to perform quality. That's the whole idea is we didn't QC that thing. So was it actually a problem?
It's a very straightforward feature right there. How long since he last was QC? I suspect it will become a very strong predictor.
Yeah, and so they mentioned that, and that's why I was wondering if this part might even fit in the model or maybe something different. They mentioned like even if we have an A+ worker that never gets QC'd, every 30 or 60 days at some random date, they should be QC'd as like, I need to pluck them out of the crowd and just check. And so there was this thought of, even if you keep telling me no, you need to build into it some factor that says, I've said no so many times, just QC this guy one more time as a spot check and feed that data point back.
No, you just make that a feature, number of days since QC.
But then I assume
Well, you have to have a positive.
right.
Yeah.
So you have a number of days for QC and then zeros on everything else. And it's always one when that feature gets taken into account. Or you pull that out of your data set
That's what I
before
was
you
thinking,
run the
yeah.
model.
Pulled out.
Like that's a special case exception. That might not even have anything to any bearing.
But you would want to use the result of that random selection, like it's TSA's random screening algorithm, right? I've decided to randomly screen you.
I've randomly decided to screen you because you bought a one-way ticket.
And so they do the screening, and then, so they randomly screen something for QC, and then I think we want to feed the result of that QC into the original model to say, hey,
Well,
this person.
it's just new data that our model continues to be trained.
So you want, so I don't know what the process of QCing one of these workers is, but you want to.
Well, it's not QCing a worker.
It's the work
It's
product.
QCing their work.
Oh,
The
they're
workers have
producing-
no freaking clue that this is happening.
They're
Yeah,
producing
they
a
just produce
document
work.
effectively. Just
Yeah.
think of it as a document. They're producing a
So
document
what
that needs to
you-
be QC.
What you'd want to do is for like a month QC everything, and then put the results of that into a file. Do stratified sampling on that.
Well, we have
I think they have historical QC records, probably not for everything, but their current process for QCing, they have historical records.
Historical.
so we can
So you
take only the records that have a QC value.
So what you'd want is a QC that resulted in a known failure, right? Of that QC.
Right.
And so if you have whether they failed or not, you can predict whether or not they will fail the QC given these parameters.
Right.
So if you can get those parameters beforehand, then you can predict whether or not they'll fail the QC.
Yeah.
That would be, and then that is a Boolean classifier. So you could use a neural network, you could use a random forest classifier, or you use them all and then just brute force it.
And the idea that despite this ongoing algorithm, there is still a randomness that we will just pluck somebody out in QC, then that can be a separate exception that we'll do as a totally separate process.
Mm-hmm.
Yeah.
You do that in the data before. And you'd want to see like, okay, you want to predict if it will end up in successfully predicting a failure, or if it's likely to successfully predict a failure, then you go and QC them or QC their work. Otherwise, you might not QC them when you otherwise would have. Right.
But on an ongoing basis, would we have to do anything other than just keep running the algorithm? And would we predict a failure QC? Like, I'm just thinking, it isn't like detecting faces feels like a more static classification in that, like a face.
People age, right?
Yeah, I guess so. Yeah.
Some
And wouldn't you
Some
also-
people age.
You'd also want to feed back in
So,
any time that
my family was
you didn't QC
close to
something
Transylvania.
and found out that there was a problem.
That's what I was saying. I think we need to feed that back in. Yeah, something that we said, you don't need to QC it, and then the customer brings up, hey, there was a problem here. You missed it in QC. We need to somehow tell the algorithm that it needs to get better, right? Like,
Mhm.
here's an additional data point maybe we weren't considering,
Oh, yeah.
or
So-
we were guessing wrong in these scenarios. We need to go in and figure out why we guessed wrong.
You might have batches and then you might have failures in the batch, and you might predict failures in the batch, because you're not going to know by the time you're making the prediction of whether or not you should QC, you're not going to know whether the customer actually get a failure in the batch. So you can get two things you could predict is one, you could predict whether or not to QC someone based on, or QC their work based on all this other data that you
What
have.
we're really predicting is
And
whether or
predict-
not there will be an error. But in order, it's like a
Well, you don't want a false positive. Right?
Heisenberg
Yeah,
thing or, whatever, it's like a.
It's the it's the ROC, right? So
It all goes back to the.
Tanks.
it all goes back to the
What you
tanks.
don't want to do is
Tanks
miss
for everything.
But I mean, so there's also this aspect of, right, the random part of it, like just randomly picking people, whether they're good or not, whether they're predicted or not, can be done after the fact, right?
Right.
You can pick something to QC or not pick it to QC and deliver to the customer, and then, hire a graveyard shift to do QC in the middle of the night or whatever, when the downtimes come in. So it can help you could feed the model in off-cycle times, right?
Yeah. Yeah. Okay.
Does anybody else have data that they want to generalize sufficiently so we can talk about it?
And then run algorithm, produce variable importance and see what pops up.
Yeah.
So we can guess all we want, but if we say, I want to guess 10 features and now build my model, most likely we'll miss something. So you need to, like I said, maybe 1,000 features, and your variable importance will tell you these 100 are any good, and these 10 or 20 are really giving you some predictive power.
Right, yeah. I imagine we'll have less than 10 even, but.
Yeah, they have a small set that they think are
Yeah, but
important.
what you could do, for example, QC instead of having a number, time since QC it last 30 days, QC it last 60 days, QC it last year, things like that. So you will have a lot of those, and you might be surprised how one of them actually pops up. And it's all kind of like variables. And then you go into which date it was QC'd and which region, what is the climate,
Yeah.
and things like that.
I mean,
their blood sample
If
every
it was a Super Bowl night, like we need to QC
Truck sample.
everyone.
Right. No, I mean, there was an interesting output of their current process is that they added a feature to their system that said, if we are missing on QC and we're delivering products that the customer is saying there's errors in this document you delivered to me, they then go back, the salespeople get the call that says, hey, this is bad. They go back into the system and they check this box that says this is like, they have had multiple QCs that have failed in the past. They're now like a high threshold.
they're a bitchy customer. They're going to bitch at us, so they need to
They
keep
actually
the
mark
next.
their customer.
Yeah, they actually mark them as bitchy.
It's stored in the database.
Yeah, they use some nicer term, but they're basically saying they're going to bitch at us if you screw up. So the next 5 documents we produce them have to all be QC,
Yeah.
very delicate, and then maybe they'll turn that flag off in the future. In reality, I bet they turn it on and never turn it off.
Yeah.
Because, you know, and so then they end up with this inefficient thing where they're QCing everything. Like, we haven't had a problem with this guy in the last 8 months. And every single time this worker does a document, I've never seen a problem with him.
Yeah.
Like, you know, it's just, they're wasting so much time.
Well, so depending on what you're QCing too, you could actually read it. Well, so if it's a digital thing.
It's a digital thing.
So
but
if it's a
not-
digital thing, you might be able to.
That becomes a
calculate-
natural language processing problem. Like, it's a much harder problem for us to digitally process a document and decide what an error really is. Like,
Well, but you could just take a file size and throw it.
no,
in
it's
as a
not
feature.
bad. It's not bad.
You
It's,
could take all kinds of stuff. off
yeah,
of that.
it's really hard.
The number of
it's
the times
essentially,
the letter E shows.
no, it's essentially a translation. Like, it's a
Okay.
translation process of I'm taking content from one format and putting it into a document, and it's the
Sure.
source digital format is not easily processable by a computer.
I would still include like number of lines and things like that.
Yeah, we have all of that. We have all of that.
So if you do, then I mean, so I would just run it through a support vector classifier. As long as you have something that you don't have initially and you want it before.
Yeah, I guess, I mean, it's fair to say if they produced a 10-line document, there's way less chance of an error than if it's a 50
It's true. I mean, there might be a strong correlation there. That might be part of what affects your ROC curve, right? And so you're going to want to include all of those features for each of those files. And then, but you also want to make sure that you include, include the history about the person, sessions they may have had doing these things, the file itself, statistics off of the file, whatever you can calculate off the file and throw in there, and then you can determine. So that's part of the preparing of the data, right? You can generate additional features, and that's kind of like what we did with or what was in the thesis, right? Is that we took an image and then we blew it out to 4,000 features for each image. And that's something that you could do too, is that take things that seem arbitrary about the file, and then, there might be somebody that just has a tendency to lapse when a noun follows a verb after this sort. There's all kinds of weird little things that can feed into it. Machine learning is kind of designed in a way that can detect those things, and so any sort of thing that you can detect off of that, you probably the source material. Like, you have the source material, you have a bunch of information about that, you have the person that does the work. Scott's shaking his head.
If you could solve this problem, you would make a lot of money from the source material perspective, right? Like, it's a non-trivial machine task to take the source material and turn it into the document and be.
Yeah,
sure
if you-
got it.
Oh yeah, I'm not talking about that. I'm
Yeah.
just talking about making statistics or making features based off the source material and including that with your workers' statistics.
You can
because
correlate some rough stuff, file size versus document size, that sort of thing. Like, if the source
number
digital
of
format was
nouns, number of
yeah, we don't know that. We
honest.
don't know that in the source material.
Yeah.
So source material is audio.
Mhm.
So we take audio and turn it into a document.
Word document.
Right. I mean, call a Google Voice thing and talk to it and see how its
Yeah.
translation works. Like, it's not great. So
Yeah,
that's
yeah.
much harder to look at that source material and say how many nouns are in this audio.
Yeah. So
Right,
so
but
there
you can
so
look at the resulting material and say.
Yes.
run Gabber
What
filters.
what was the topic? Because the topic may have a huge.
Yeah,
role.
yeah. There's definitely a natural language processing problem that could be applied to the output material,
Yeah.
and maybe something comes out of that. Like you said, how many
So-
repeated nouns or something.
Gabber filters. So you can run those on there. So that seems, so the Gabber filters are the things that are used to detect wavelength changes in the image of the faces, but that was what they were originally used for. So you could produce data points off of Gabber filters, or if you can find out how Spotify is doing their, not Spotify, what is it? Shazam is doing their audio.
Recognition.
Yeah, what they're doing is they're classifying their audio. They recognize a song or something like that.
I
based
think
on
they're
their
doing
data.
a lot the same way that Pandora guesses what they want to play next, right? Like, they're stripping out the contents and they're guessing based on pitch and tone and background vocals and this is a female vocal with
They
a melodic
create
tone.
only like 4 or 5 features from a single song out of it, and it's really quite. And then they use that to run predictions on it. It's really impressive. Yeah, so I would keep that in mind. So produce additional features off the source material, get a history on the person doing the work, and then you know, but ultimately, I mean, you don't even need to do any of that as long as you have something now that you won't have when it's too late, right?
Yeah, that's what it comes down to, is we've got a set of data right now. We want to just brute force a couple of things. That's why it's interesting to see how you go in and just slam some things at the data real quickly and see if something.
So just go on that GitHub
honestly,
and do this.
Yeah, honestly, it's like, give me a 25% increase in efficiency with my guys, and that's probably all that, like, that's the best bang for this customer's buck. Like, I'll pay you 25% increase, save you so much money. That's as far as we need to go right now. Don't go crazy.
Yeah, and that's part of what you're going to do. So it's the same, just like security or just like a problem like this. You can spend an unlimited amount of money on it and continue to improve and continue to improve, but eventually you're just going to want to call it off. Is HTTPS, over SSL good enough, or do you need TLS, or do you need some sort of encrypted stream that goes back? And so there's all kinds of stuff that, do you need your own cryptographic, you could pay a cryptographer, a huge amount of money to make your own machine. Yeah, exactly. And so that's where you're going to talk about, well, how much money do I spend on doing, actually doing the machine learning? Google spends an exorbitant amount of money on it. But somebody else might not need to. A smaller shop might just say, okay, all right, we got these 3 different classifiers, whichever one performs best, we're going to deliver. And that might be good enough for you. And you might not need to spend a whole lot of time doing it. So practically you could do what I just did to the data. Because I mean, right now, I even narrowed it down to the column that I wanted. So the nice thing, so I would do a little bit more to the data than this. You'd run a feature elimination step through sklearn. So like that'll just eliminate features and give you the features that you want to actually learn off of. It does all the calculation to figure out which features are important. All of chapter 2, there's like 1-line functions in sklearn that'll do them for you. And then basically you do feature elimination. You'd run it against a few different models that you like, and if you get something good, you go with it. If not, then you're going to you can really spend some time and some money on it. And then finally, if you're like totally at a loss and you just really need to go crazy, using evolutionary algorithms are fantastic. So
at that point, I have to read your thesis, right?
Yeah. At that point, you go to my thesis and you look up differential evolution, binary particle swarm optimization, and so, but basically what evolution algorithms do is you actually create, so genetic algorithms, easiest to explain because it resembles human genetics. So you have a genome, which is a huge binary value, and then you take
Binary?
Binary. Yeah, so we're 1s and 0s for the genetics, for our gene. So
No, we're talking about machine learning genetics.
Machine learning genetics. No, we're talking about a genetic algorithm, and so you could have 4 values by having the 2 binary, right? The combination of the 2 binary. But we're taking a binary string in a genetic algorithm. This is how genetic algorithms work. Okay, we're taking a binary string that represents our genome, right? And we we have a population of 50. We make 50 of them and randomize the 1s and 0s. Then what we do is we determine if our fitness, which is our AUC for the model, is, in this case, like so let me back up. Genetic algorithms can help give you a good enough solution to the knapsack problem in less than 1% of the computation time than you would to.
Yeah, what was that problem?
So the knapsack problem is, or the traveling salesman problem, or so what
NP
the idea,
problems.
yeah, NP complete problem. So if you have an NP complete problem, you can use genetic algorithms to quickly give you a good enough solution. And so what that means is that you might not have the perfect solution, but you'll have something much more elegant than something that if you were checking sequentially, you'd find in a million years, basically. So what it does is it takes those randomized values. You say, do we want to stop because the fitness is good enough? No? Okay, well, let's go and we'll take the best fitnesses and we'll promote them. Then we'll take the top 2 and we'll start mating them. And so you take the,
That's why it's called genetic?
Yeah, it's called
Okay.
genetic. And so you start mating. So you take random sections and you combine them at different points. And then you add a genetic mutation of 5%. So meaning that 5% of all of your offspring will have a genetic mutation in them. And then you run that through the genetic algorithm, and eventually, you say, do this for 100,000 generations. And then by the time you come back, you'll have
Shakespeare.
Abalone.
Shakespeare, yeah. So you'll have abalone evolved out of it. Probably abalone is probably more complex genetically than we are. So that's what's cool about these algorithms. So what you could do is you could use them to configure various machine learning models, and that's kind of what I did for this thesis. Is I took binary particle swarm optimization, combined it with differential evolution, and got differential evolution. Binary particle swarm optimization.
Building's kind of easy.
Yeah,
You have a
yeah.
Machine learning model to program other machine learning models.
So the difference between genetic algorithms and binary particle swarm optimization is it's called a swarm because you say, okay, this is like 100 birds, and you just throw them out there, and then the birds go to local minima and maxima. They actually travel around in the hyperdimensional space, and then they find places that they like, and then they go there, and then if they've been there for too long, they're kicked off to somewhere else, and so they explore to try and find the elite values out of it. So it's really cool stuff. And this is another type of evolutionary algorithm that's not the genetic algorithm that I use. But anyway, it's a lot of fun.
Man, you must have got so many chicks in college.
Yeah.
Believe it.
Swarms,
Talk
yeah.
about genetic swarm algorithms. Magnet.
You just take the binary part? Yes, no, okay, I'm gonna go next, yes.
You're just evolving.
Yeah.
Hey, Chris. Can I take you to this
So,
question
so how's that roommate that nobody else can see?
Yeah.
Harvey's fine. He says hello.
Yeah, okay, so anyway,
Okay, so time check.
Yeah.
We're just about
What do
8
we
o'clock.
want?
So we should chat a little bit about. So we should get some feedback on who was able to do the learning or the reading. Bill said he was able to do it. Anybody else get through the reading, and did you get far enough in the reading to start to look at the different data sets on the UCI data set? That was kind of one of the other goals: do the reading and then look into all of the data sets. And this is the kind of really loose part for us that Chris and I have been talking about. Is just how do we get a practical application of the learning? We can sit here and we can talk about it. It's very interesting. We all have kind of separate problems, but the data sets are out there in a way that we can start applying algorithms to them. But we're not sure exactly what value that produces. So we're wondering if anybody had feedback, if you looked at any data sets, you had some ideas on if all of us independently went home this month and this month and next month and worked on this one data set together and we were trying to answer this one question maybe or something like that. I'm not sure where we want to go with it, but we were hoping to get some ideas on what you think might be useful. I mean, if you haven't been to other TIGs before, what we usually do, and this one's a little bit different because it's a little bit harder to do that, is along with the book, there's usually either an online learning segment where there's existing videos with exercises, or the book has exercises in them, or we create the content. So we would create, coding exercises and people can do them. And then we have some concrete code that we can all talk about. This one's a little bit different. We don't quite have that. So we're trying to think of something similar where, if Chris comes in and shows some code, or one of you can come in and show some code and say, hey, I did this. Can we put my code up on the screen and kind of walk through it? And then everybody's kind of talking about the same thing, or at least the same data set, or trying to solve for the same question on the same data set. And I used this algorithm, you use that algorithm, we can kind of compare. So does anybody have any thoughts on that? Did anybody look at the data sets and find one that was particularly interesting? Abalone, mines, irises?
Yeah, so there were
Fascinating stuff.
There were two that I had looked at. The first one was the default of credit card clients data set, which looked like it would be interesting. But when I looked a little deeper, it had this line. Among the 6 data mining techniques, artificial neural network is the only one that can accurately estimate the real probability. And
there's
I
no
felt
ANNs in this book.
that's
Gave it away.
just not going to get us there. So the other one that looked interesting was the poker hands.
That's cool.
Well, we could do a neural network. It's just not in this book. I know that was in the $80 book.
Yeah.
Yeah, that's
You
why I
gotta pay
said
extra for the neural network.
I don't think we're going to do that one.
So the poker hand one is interesting, yeah. And so that was predicting what the hand will be. But basically, you know, so you can place your bets, right? So you can bet accurately and predict what you're gonna get dealt. And I suppose predicting what other people are holding too.
But the idea would be to choose a data set that lends itself to the approaches that the book covers, I assume.
Yeah, any of the data, it would be good for we can cover any of the data sets in the book. Although, I mean, I don't know, we could even challenge the credit card fraud one and try it with different algorithms that are out there. I'd love to see, so one side project that I've been wanting to do is to make a scikit-learn wrapper for TensorFlow. But I don't know, I want to put that on GitHub at some point, but I don't know, anyone knows, that's the neural network that's out there and it's available and free, so.
So poker hands is cool. I mean, one of the things that I think would be good is that we pick a data set that's manageable in size and the questions that we can ask about it are manageable so that you're not like Chris said, you can go on and on and on forever, constantly changing models and, you know, the practicality of that maybe isn't that useful.
There's only one paper published on this.
Right, so we want to get something like poker hands could be a good one. I like that. It's like, you know, there's a finite number of questions we really realistically want to ask about this data. And we're all familiar enough with the content. Like, I barely even knew what the hell an abalone was, so that data set's not going to help me. But I know
now.
I do know now. You know, but poker hands, everybody's pretty familiar with that, so you would be able to quickly tell whether the results you're getting make sense or not. Right? So that might be interesting.
So is the idea to have, say we choose poker?
We have no idea what the idea is.
Oh,
That's what we're asking.
Because it seems to me that, like, if it's true, and correct me if I'm wrong, that 80 to 90% of your work is actually getting familiar with the data and learning how to use it, like what's useful about it. Like, it might be useful for us to choose one data set and become very familiar with it. Or I could also make the argument to say that maybe we should choose like 3 or 4 data sets and become familiar with all of them to compare and contrast how you make them useful, how you identify what's a good feature and what isn't, you know?
That's interesting.
We could try and do kind of a stage thing where we say, you know, first we'll try the poker hands, see if we get a response from everyone, and then come back and it's like, okay, next meeting we could say. I don't know how many more meetings we have scheduled for this. But.
Yeah, I think realistically it's probably two more.
It's not a very long book.
Yeah, so it's probably probably 2 more after this. So next month and the following month, and we'll probably wrap up. So we'd probably like to have, you know, on the last meeting, we'd like to have some culmination of the exercise or exercises that we did that people are able to discuss and say, you know, here's the problem. And hopefully, if we can determine something this month, then next month you'll have some questions around. I start playing around with this data set, or I start playing around with these 4 data sets, and hopefully some questions in between too. So, but yeah, realistically, I think you probably have 2 more meetings left.
Chapter 3 is on predictive model building. Talks about big data and stuff.
Yeah, I think we'd probably do another 75 page. I think we did roughly 75 pages, 7,500 pages, wherever. Then probably chapters 3 and 4.
3 and 4 would be the right page range, but 5 builds on 4. And then you've got 6 and 7, which sort of take you in another direction.
Yeah.
Is the big data topic really even going to be something we're going to delve into here? I mean, because like the data sets we're talking about are not really going to require.
Well, I mean, he provides big data sets too here, but I don't know. I mean, it's really whatever we want to cover.
Yeah, it's up to you guys, really. I mean, we're relying on Chris's knowledge here and heavily taking advantage of him. So it's up to you guys how much you want to use his knowledge. But we also, you know, we're respectful of everyone's time, and we also know that, like we said, the attrition rate and the TIGs, they tend to drop off as people get, as the topic runs long. I think we had an entity framework topic that went 8 months or something, and it was just like, wow, we had beaten it to death. You know, the entity framework book is 500 pages or something. So,
wow.
And at that point, everyone was over it. So we're trying to shorten them up a little bit. And we've been doing Python for 8 months probably, or kind of have done Python for 8 months. This is the 3rd section of Python, between Python the language, Python on the web. This is Python data science, and we're pretty well beaten down on Python at this point. So,
well, I get the impression, at least from the 2nd chapter, that the code that he's giving out is mostly for explanatory purposes. There's more efficient and easier ways to write that code.
Well, yeah, there are more succinct ways of writing the code.
Yeah.
But that 2nd chapter is mainly just illustrating how to prepare the data. In later chapters, he actually talks about running the model and getting the AUC out of it. But I mean, really, when we were talking about a competition or something where we try and do a better prediction than everyone else, that could be something where once we cross some threshold, and in reality, we could simply use the code that we have on GitHub, which might be better, is maybe fork the current GitHub repository that I have there, and then take it in your own direction with the poker data set, and then see what you can do to get the best result. So
Yeah, but poker is really interesting to me because I could see us spending the next 2 months tweaking the data set, you understanding what features matter, what don't, running algorithms, getting it to the point that you want, and then bring in a deck of cards and play poker, and you use your algorithm and see who wins. Right? There you go. Right? Because that's interesting. Then it's like a practical application. Go play 5 hands of poker. You use your thing, run your tool, play your hand, and let's see who wins, and whoever wins.
That'd be a lot of fun.
Yeah, I think that'd be cool.
That's a nice idea.
I think we know somebody who used to be a dealer.
Yeah.
Yeah, I like that. That's a cool idea. Then we've got some application to it, and it's fun. People are interested, and and we'll give away, I don't know, one of Chris's succulents or something.
Nice succulents.
Yeah, you get some.
Giving away an abalone.
Yeah, that's right.
Oh man, I don't know if I can.
Only if you can guess
cash
it.
on
That's
this
all.
group.
Actually, we're gonna give you a box. It's gonna be a rock or a mine, and you have to decide. Second task is should you open the gift we have. All right, so I like that idea. I think that's cool. Yeah, I think that's cool. I think that gives us some.
So
Poker data set seems limited, like we won't go on forever, but there's some concrete, like I am doing better than you by winning more hands type of thing. So.
Okay. Well, do we want to try and maybe take the code on GitHub or the code in the book and try and have an AUC that you were able to achieve since this meeting?
Okay.
Maybe.
So take what?
Either choice, right?
Yeah.
So that's your first decision. Take the GitHub code or take the book code.
Yeah, I think it's up to you. I think if we say we're gonna standardize on the poker hands, and the goal is gonna be on our last meeting, we're gonna play poker, and whoever wants to participate will use their algorithm, and we're just gonna see. So it's up to you to tweak your algorithm, try whatever classified, do whatever it is you want to do to try to get the best results you can.
So we need at least more than one, right?
Right.
Otherwise,
a couple
they bluffed their way out of the competition.
Yeah. Well, I think we have at least 4 of us, and or 3 of us will play or something like that, and then maybe we'll leave Chris out. He's the ringer. He'll kill us all. And we can break it up, right? Like if we have a bunch, we'll just have 2 groups of people playing poker, quickly.
Tournament style.
Yeah, tournament style 5-hand. Yeah, and then we'll use a genetic algorithm to weed out the people who are losing.
Yeah.
And then you got to go in the back and mate, and then your offspring becomes play poker. It's very complicated.
So
This is all going on to the microphone.
Yeah, of course. Our hangout just spiked in viewership all of a sudden.
What's going on? People are talking about particle swarms.
Yeah.
maybe we
Yeah,
can
I
make
think-
that into an audio clip and then play it for Brad every
That's
once in a while.
That's a cool idea. I think one of our original takes at the very, very beginning, we broke into smaller groups and people kind of like that. And since then, we've kind of stayed away from that. So I think it'd be good to kind of.
People liked it, so
We stay away.
So tried to stay away from it.
Well, there was a bunch of issues that didn't work, but I think playing poker in small groups would work and using your algorithm, so intend to
Tournament.
bring in a computer or something you can run your algorithm on that meeting. That way you can play, and then we'll get decks of cards or have people.
No. It shouldn't be even decks of cards, right? It should be a computer program.
That's not as fun.
No. I'm saying like,
Make it physical.
a deal, it'll be.
So you just type in your hand and then
Yeah,
and then you run it and
I
then
like
you
the
use the
physical part
prediction to actually play.
Because then you could eventually build it in a mobile app and you can put it on your lap at the Vegas casino and then you could actually be winning. I like
They
the
don't
idea of
never
physical.
stop
It's more interesting.
Yeah.
I like the idea. I'm fine dealing cards. Anyway, we'll sort out the particulars, but let's go with the poker hand with poker data set with the goal of playing poker in 2 months and seeing who wins the most hands.
The result is only going to be the percentage, right? So
Yeah.
his algorithm like 60%, but mine like 70%. So
Yeah.
it's
Well,
like,
no, that'll be the accuracy or the AUC of the algorithm, but then you use the
Yeah.
algorithm to make predictions.
Yeah.
So you learn the data and then you make predictions on the data with real
Now you
with
say,
real
and-
hands.
And so no one knows that data, and
Yeah.
furthermore, it's random. So
right.
So I'm
So
gonna,
even if yours is 70 and mine is 54, there's a chance that I might crush you.
right. So the end goal is you use that tool to make a prediction whether you're gonna play that hand or whether you know what he has or that what.
So are we keeping everybody's code secret from each other? Or like, how are we gonna do example? Like,
No, I don't think so. I think everyone, I think you should be able to share it and whatever. And
because we could
It's up to
offer
you to-
help for it in front of everybody here.
Yeah, I think
That
it's
sort
fine.
of thing.
I mean, I expect that some people will have identical code or very similar code, and some people will have wildly divergent code.
That's why
We'll see. It's an
that's why I think
experiment.
if we had like a simulation type thing where we could hook it up and like
Have
let's
us play
run
a
through
million
3,000
games.
hands of poker
Yeah.
real quick.
I was
You
thinking.
know, like
Let's
just
go.
go.
Okay.
And 3,000 hands are over, and you dropped out after 165 hands because you're bankrupt.
Sure.
Okay.
Yeah, we can figure out the particulars.
That's what they were
of how to-
saying during the TED Talk, right? So during the TED Talk, they're saying that machine learning is going to turn into Skynet off of a chess game that just wants to play chess. And so they're saying it creates a model of the world. It's the most perfect chess game in the world, right? And it creates a model of the whole world to determine whether or not what your next move is going to be. So it'll predict where you're going to go home after the game, and this and that. So it'll use that information to decide what to play. And so during that model, it predicts that it will be turned off and it won't be able to play poker anymore unless it stops all humans from turning it off again. And so the chess game ultimately becomes that's why everybody's freaking out.
And the movie by Michael Bay. Is
Yeah,
Checkmate.
exactly.
2017. The machine.
No,
Exactly.
Yeah, exactly.
In a world where
Rooks killing bishops all day.
Back to that mating thing again.
Yeah,
totally.
exactly.
So are we talking about for next time, in addition to the poker thing, we're talking about reading through 3 and 4?
Yeah.
Although you made a good point that
Yeah,
five, 4 and 5 are kind
five
of,
is
Five's big.
yeah.
and way.
In reality, I think Bill might be the only one that did the reading, so we tried.
I read 2.
So we could say Bill read till 5, or so let's do 3 and 4 and start working on your poker hand player.
Right.
Yeah, get to if you can get to a point where you get an AUC back, like that would be good, because that way you'd find any stumbling blocks they'd have, and then you can start tinkering with it, right? We'll talk a lot about tinkering with your model,
And you guys probably all have decks of cards at home you can play, or you can write a little simulation to play, test your model, get it all.
or you can call Scott and you'll make a simulation and you just upload it to a simulation and then it'll play for you.
All right. Any other questions before we take off? Chris is going to post what he's got to GitHub. The last month's already there, so check the meetup.
Yeah.
So not much GitHub. Not much. It's
It's just one
tweaks.
file, but I have the new file and then I have the new code in a separate file.
Yeah,
So you'll have what we had last time and then you'll have what we did today with the rocks versus mines. So
Rocks versus mines.
And next month I should get the meeting scheduled early enough, but it's always the fourth Wednesday, it's 6 o'clock here, it's always the same time. So if I screw the dates up, don't.
Right, so I see that as being March 30th. at this
Sure,
time.
sure.
Wednesday, March 30th.
Sounds great. No idea, but that sounds right.
Can I ask about the feature elimination?
Yeah.
That was kind of interesting. In the book, it was talking about, okay, feature number 35, if we predict on that, we get good prediction.
Yeah.
So should you burn calories trying to only doing feature number 1 and see what you get from that? Only do feature 2 and then try combinations?
So
Or does the
yeah,
model do that for you?
so combinatorial math gets very big.
Oh, yeah.
So if you have 100 features, you're talking about, choose 99 possible combinations of things. And so what you'd want to do instead of that is use one of the algorithms that people have come up with to do feature elimination. So one of the most naive ones out there that is commonly used is what's called one look ahead. And what it does is it just says, okay, well, use the first feature. Now use the first feature and the second feature. If the prediction wasn't better, then eliminate the second feature. Use the third feature. If the prediction was better, include it. And now you pick the third, fourth one. So it only does it n times, or you only do 100 iterations rather than, some billion iterations or whatever. And so there are a number of algorithms in sklearn that'll do it for you very quickly. There's like a support vector machine-based algorithm to cut out features as you do them. And then there's other special algorithms that you could write yourself or that are out there as well. There are a ton of research papers out there. Like you look at the bottom of these things and they talk about this, but you know, a lot of us don't have access to a lot of those like common publication areas. So just finding those feature elimination techniques that are fast are probably the best way to go first. And then if you really wanted to brute force it, you could. But so my thesis, I multi-threaded my thesis and I ran it on at least 12 different processes at all the time and ran it for a month.
Wow.
And so to run the genetic algorithm to automatically find the best model. And I ran through neural networks, I ran through all the different models, I ran through all kinds of stuff using the genetic algorithms for it. And so the whole thing ran for about a month on 12 individual processes and to choose those things. So I suggest just going with one of the pre-baked ones, and then, you know, if you find yourself wanting to spend more time, go ahead, but first use the easy wins, right? So like do it without feature elimination, then add a really simple version of feature elimination, and then increase on that until you want to get more and more specific.
But it is potentially better to eliminate like the noise. You want a higher signal to noise.
Yeah.
As much as possible.
Exactly. Yeah.
And
And there are ways to get that.
Scott pointed out the fourth Wednesday next month is actually the 23rd.
The other one's
the fourth.
The other one's
not
the
the
fifth.
last.
Yeah, it's always
See, this is why I wanted to say it. So,
And it's
you
in
know.
trouble.
Fourth Wednesday, so it'll be March 23rd. And we'll get the meetup up there at some point.
All right.
March 22nd.
March 22nd.
Just check requirements for the customer.
That's right.
All right, thanks for coming out, everybody. If there's excess pizza in the back, feel free to take it with you, otherwise it ends up in our. I think if you don't mind folding your chairs up, that would help us. And if you really want to help us, you can throw them in the back. We'll see you next month.
So